Welcome back. Let's take a look at, I hear a beep. Let's see, where did that happen? Participants. Here we go. Admit. Oh, I think I'm going to sneeze. Right, everybody's here. In that case, let's get started. The nice thing about second semester is everybody's familiar with my teaching style, and the Brightspace course is organized roughly the same way. I might have moved a couple of things around. I tried to put some things out in the table of contents where it was easier to get to rather than having to dig through the Start Here menu. So everybody knows how to get to, let's see, I've already been there. My New River. Okay. D2L, I've already started that too. It should be over here. Here we go. All right. Tutoring. Barry Pine is going to be tutoring again this semester in case you need help and I'm not available. Or if you just need another perspective. Let's see. I'm an instructor. Let me make myself a student. There we go. That's not supposed to be there. That was last semester. Okay, well, I've rearranged the mini bar a little bit. Anytime you want to go back to this page, just hit course home. Everything else is pretty consistent. Content, assignments, quizzes, grades, and Zoom, class list. The rest of it I made lower priority. So if we go into content and hit table of contents to back to the beginning, I think syllabus is out here in the table of contents now. Contact information is there, textbook info. I've added a quiz. This is college-wide. We have a quiz, and this course introduction quiz is simply 3 questions. And it doesn't require Respondus or a lockdown browser. And they're just 3 questions. Just to confirm you've read the syllabus, that you know that you're responsible for all fees, tuition and fees, presumably above and beyond what your financial aid is covering. And then the last one is a question on artificial intelligence. And this will require that you've already read the blurb on that. It's in the syllabus, and I extracted it and put it in the main menu also. So let's go back if it'll let me. Come on, there we go. So if we go back to table of contents and down, AI usage in this course. This is my my blurb. Faculty have the option of either completely just saying no AI in my course. I don't know of anyone that's doing that. Or it's a free-for-all. I don't know anyone that's doing that. Most faculty I've talked to are doing middle of the road. They're just saying, this is what I allow, and these are instructions for ethical use of artificial intelligence. So you have to read that and then take the quiz so that you can answer honestly all 3 questions. Well, you have to read the syllabus too. So the quiz comes after you've already done this stuff. Let's see, I'll come back to the syllabus in a minute because I want to take a closer look at some things. This semester, we're doing the same thing as last semester with the textbooks. You have access to Cengage Unlimited because of a college contract with Cengage. They probably bumped your fees up a little bit so that we could cover the cost of doing this. But overall, it's cheaper. And it cuts out the delay that many students are experiencing with trying to get access to their textbooks and not getting them for a couple of weeks. So all you have to do is, like before, go in to the course, and I'll show you where that is. You probably will recognize it, and enroll in the course in Cengage, and that'll give you access. If you've already got an account with them, they probably won't ask you anything. They'll just take you right into the course. The homework and the textbook available. And this is that link. I pulled it out into the table of contents also. Let's see. Cengage again has troubleshooting hours for any problems that you might have with connecting to their services. And you have to go in and click on this link. And then you have to decide from that, you're going to the Cengage website, and then you have to pick a time and a day. Okay, the rest of this stuff down here is standard required stuff from the school. That's why I put it at the bottom. And then we go into the usual place to start here. But you can get to the syllabus from here, or you can get to the syllabus from here. Let me do the syllabus first. Call it up. There it is. This all should look familiar. Let's see. Textbook, learning outcomes, all that stuff. The same general grading scheme, 10-point scale. The way the semester is structured, because we lost a whole week at the beginning because of Martin Luther King Day, I'm not going to have a final exam. There's just not enough time. So we'll do, let's see, chapters 10 through 18, I think. Yeah, chapters 10 through 18. It's 9 chapters. Will be chapter exams. The first one is on chapter 10 and 11, and then there's one on 14 and 15 for acids and bases and buffers. The rest of them are single chapters. Homework again is 20% attendance, which you get credit for today. And then the crosswords. I don't have any other special extra credit exercises like we did the first semester. So all the independent extra credits are crossword puzzles. Of course, the exams will have some bonus questions embedded. Let's see. I do have, there's a blurb in here, should be on artificial intelligence. It might be later. Oh, there is, if any of you need it, there's a counseling service that's provided by a grant through the state. It's called Better Mind, and here's the connection. You can also get through it through the our main webpage. Just go to Student Services and you'll find it there. But this is a quick and easy way to get there. If you have anything that's bothering you, whether it has to do with the course or not, it doesn't matter. You can get counseling services from this from one of their social workers, and it's completely anonymous. The school doesn't know. I don't know. There's no accounting given with personal identifiable information. Same course materials you're going to need, and there's a general outline. You're all familiar with the way I do exams and homework, attendance policies, bonus and extra credit. Those are just in there for posterity's sake. Here's the schedule. Today, I'm going to get through chapter 10 and 11, introduction, and that's why there's no lab, because it's probably going to take the whole 4 or some odd hours to get through it. And then next time we meet, next Monday, we'll review for the first exam, and we'll take whatever time is necessary to talk about the lab. I may say a word or two about the lab if we have time today, but it's not on the schedule. And then my pattern is, as usual, no labs on exam days. We'll do the exams, and then I'll introduce the next material. That's the way it has to go with these with block scheduling. Block scheduling just means there's one class a week, and it's a long one class. So we don't have any choice but to introduce material right after the exam, and that's why we don't have a lab on that day. We don't have a lot of labs, right? We've got five labs, and there's one of them that is not a formal lab report. This Le Chatelier's principle. It's just a fill in the blank, answer questions. But the rest of them, the other 4, are formal reports. So you know the routine there. Let's see. Spring break is for us will be on March 16th, and that's the day that midterm grades are due. And there's the last day to withdraw is April 17th. And like I said before, there are no final exams. Okay, let's see. Here's the artificial intelligence blurb. It's just like the one that I showed you earlier. And the rest of it is pretty much the same. I've got an appendix there. If you take the this is homework. Appendix 1 is for homework. Appendix 2 should be for taking the exams in Brightspace. And the policy is the same as before. If we don't have an exam, you can Zoom the class. I mean, not if we don't have an exam. If we don't have a lab that day, you can Zoom the class. But since no labs are on exam days, that means you probably want to take the exam in Brightspace, which is fine. And if that's the case, if all 3 of you take the exam, don't come to class and take the exam in Brightspace, then I'll just jump right into the lecture. But I'm flexible. Okay, let's see. Do I have another? That's all familiar stuff. Oh, Zoom attendance. Okay, so they're the particulars for Zoom attendance. All right, that's it. Any questions about the course so far? That's the syllabus. And let's go back to the table of contents. And I'm looking for things that might be different. Let's see. We'll go to start here. There we go. I pulled the schedule out so you don't have to go digging. There's your connection to the ebook. Everybody's probably got PDF readers already. I had one student I found yesterday who paid for a reader, and I had to break the news to him. If you pay for a PDF reader, then you've been scammed, because the readers are free. If you want to edit PDF files, then you either have to buy the full version, or there are available PDF editors out there, but you have to learn how to use them. That's all. Okay, let's see. Those are our learning modules. Let me collapse everything first. Here we go. They're the learning modules, and they're organized as usual. Let's see. Well, there's practice test. You guys have already taken the practice test, I'm sure, or you've gone through a semester using Lockdown Browser and Respondus, so you probably don't need that if you haven't changed your equipment. So this is what we're going to be involved with today. I got a checklist in this one. I don't remember if I put one in the in 101, but there's a checklist just to keep you on track. Then you have your PDF files. They're located here, and PowerPoints in the review, and then you have your videos. And I'll do the same as always. I'll replace this with the most recent one. Hopefully I'll get to replace this one with a bona fide one. Last semester it messed up. Well, actually the semester before is the last time I recorded this one successfully. Something went wrong with the lecture this past fall, so that's why this one is from February. Anyway, no, that's not right. I didn't teach this course last fall. That's right, it's last spring. Homework video archives. Let's see, what else? Area crosswords. And I think all the due dates are correct. As usual, if you find a conflict between a due date in Brightspace and a due date in the syllabus takes precedence. And just call my attention to it so I can fix it in Brightspace. All right, so those are all your modules. Supplemental documents are, some of these I'll give you as handouts. If you want to wait till next Monday, then I'll have all the handouts for you. But of course, if you're going to review, you probably want to at least download the review for chapters 10 and 11, so you'll be prepared for next Monday's class. That's it. Any questions? No? Is anybody there?
Yeah, I'm here.
Okay. There's 1 out of 3. Actually, in baseball, that'd be a good batting average. I'm batting 333. Okay, so I'm going to jump into. Wait a minute, there's a chat. Oh, okay. Olivia's mic doesn't work. Okay, that's Olivia. What's Matthew's excuse?
I'm here.
Okay. It's nice to know that there's an audience out there. And as usual, stop me if you have any questions. There's nothing special about Zooming the class from home. You can still interrupt me. Okay, so I'm going to stop this share, and we're going to, let's see, share chapter 10. All right, so let's see. I want to make this into a slideshow. There we go. All right. So chapters 10 and 11, actually, remember we finished off last semester actually trying to understand the chemical bond, what holds molecules together. And understanding those bonds is key to understanding chemical reactions. But physical changes, physical properties and physical changes are also dependent upon wait a minute, I lost my train of thought. Chemical properties and reactions also depend upon physical properties and changes. They influence the way the chemistry proceeds. So we're going to take chapter 10 and 11, and we're predominantly in the physics of what's happening in gases, liquids, and solids. And that involves how do molecules interact without actually reacting. Okay. We call those, well, we've studied already the intramolecular bonds. That is, within the molecule, between atoms in the molecule. And when we're talking about a molecule, we're actually talking about sharing electrons. These are covalent bonds. We will approach ionic bonded solids also. But when we're talking about molecules, those are covalently bound atoms. What we want to talk about now is forces that are attracting or repelling, as the case may be, molecules to one another. In other words, intermolecular forces. And those forces are arranged in strength. In other words, the strongest forces will be ionic. But if we're talking about molecules now, then we go to forces between molecules that have partial charges, the dipole. And I know we've introduced the dipole concept probably with VSEPR and structural molecular structures. So if two molecules have dipoles, then they will orient themselves so that the negative side of one molecule is attracted to the positive side of the other. And those dipoles are on a continuum of strength. In other words, they're very strong dipoles and they're very weak dipoles, but they're permanent. The molecular structure and the atoms that are bound together determine this the magnitude of the dipole. And the stronger the dipole, the stronger the intermolecular forces. Now there's one that is pulled out of this group and marked off as the strongest, called hydrogen bonding. And when you have a molecule that has a dipole moment, if there are hydrogens involved and attached to atoms of a certain my mind's gone blank again. Electronegativity. Certain electronegativity, the hydrogens are bound to that atom, then you have the potential for hydrogen bonding. And those atoms are either, let's see, nitrogen, oxygen, and fluorine. So if you have a hydrogen bound to any one of these, and you can have Well, if you have that, then that's all there is, because you can only have a single bond with a fluorine, but you can have two with oxygen or three with nitrogen. And that gives you a very, very strong dipole. You have positive here, positive like that, and you have negative on this side. And the strength of that dipole is very, very strong. We'll talk about that more in just a minute. On the continuum of dipole strengths and intermolecular forces between molecules, the next are those molecules that don't have a permanent dipole. For instance, if you have two of identical atoms bound to one another, and the perfect example there is nitrogen. Right? There's no possibility for having a dipole there, but there are attractive forces between nitrogen molecules in pure nitrogen. And the reason we know that is because nitrogen condenses into a liquid if we get it cold enough. And in order to be a liquid, there has to be some attraction between the molecules. So, and in some places in the solar system, we have solid nitrogen in the outer planets. But we have to explain why those molecules attract one another if there's no permanent positive negative charge, partial charges. And we're going to talk about that more in just a minute. Now, one other, it seems logical and it seems almost silly to mention it, but ask yourself the question: which of the two, intramolecular, that is inside the molecule, or intermolecular, between the molecules, which ones are stronger? Put it this way, do an Einstein thought experiment. What if the external, the intermolecular bonds between molecules were stronger than the bonds inside the molecule? What would happen? Molecules would get ripped apart, right? If you have stronger forces outside than you do inside, you would have no molecules. They just get torn apart. So logically, and this is experimentally proven, of course, the intramolecular bonds are stronger than the intermolecular bonds. Now, here's an example of hydrogen bonding. Now, I hate to use the word quintessential, but it seems to fit. Hydrogen bond is water. How does water interact? We know the dipole, water has a dipole. And in fact, when molecules accumulate in water, they have a very strong intermolecular force, hydrogen bonds, that hold them together in liquid at or below 100 degrees Celsius. Now, if we look at the periodic table, and you look at the hydrides of the oxygen group, the chalcogens, you could have water, you could have hydrogen sulfide, you could have hydrogen selenide, telluride, all the way down, and you look at the boiling points of each one, they follow a pattern. As you go up in the group, the boiling point decreases until you get to water, and then the boiling point shoots up. And the reason for that is hydrogen bonding. Now, there are two reasons that hydrogen bonds work. One is the electronegativity difference between oxygen and hydrogen, nitrogen and hydrogen, and fluorine and hydrogen. That's number one. The other is distance between the molecules. Notice that hydrogen is attracted to oxygen in this case. Well, how big is hydrogen? It's vanishingly small because it's just a single proton. It's very small, which means that the oxygen from a neighboring molecule can get very close to that hydrogen. Remember, the force of attraction, according to Coulomb, is dependent upon the size of the charge, in this case, only partial charge, and the distance between the charges. So the closer you can get to that positive side, the stronger the attraction. So those are the two reasons that hydrogen bond is the strongest, intermolecular force. All right, we covered this already. And there it is in blue letters. Okay. Now, I mentioned in my description of actually, I didn't go into enough detail. The molecules with no permanent dipole are attracted to one another because of this concept called London dispersion forces. London is the name of the scientist who proposed the idea. And dispersion has to do with the distribution of electric charge in a molecule. In small molecules, the dispersion is not that great because the electrons don't have much room to move around. But it does exist. And if we go back to our example, let's say we have two nitrogen molecules approach one another. What we believe happens is for the London dispersion, is that instantaneously electrons in motion tend to aggregate or congregate on one side of the molecule versus another. Now, this doesn't take very long. It's a matter of picoseconds. Right? So for an instant, you get, say, partial negative on this side, partial positive on this side. These are temporary, but they occur just long enough that if a neighboring molecule is close, that this negative pushes negatives away from here to make this side slightly positive. And now that you have a positive negative, you can get intermolecular attractions between the molecules. Now, the bigger the molecule, or the bigger the atoms actually, the stronger the London dispersion forces are, because you have more room for the electrons to randomize themselves. I think I've got a chart coming up, so I don't want to steal my own thunder. We're going to be talking about phase changes. Phase changes involve these intermolecular forces. The chemistry's the same. The identity of the molecules remains intact. So these are physical processes. These are physical changes, properties. So this is the artist's idea of what you would see if you were small enough, or the atoms were big enough. So these molecules are bouncing around in a gas. They're very high energy, and very large separations. So there's very little interaction between them. There's some, but not much. That's why when we study gases, we can study any gas for the gas laws, because there's so much room between them and they interact so sporadically and so weakly that any gas will do. Liquids, on the other hand, are closer together, so the intermolecular forces have taken over, but they're not complete. They don't lock the molecules into a structure. They're free to move past one another. And then solids are locked into position. Some of them amorphous, that is, no recognizable structure, but they're still solid. They retain their shape, they retain their volume. So what we're saying is that as you go from gas to liquid to solid, the intermolecular forces are stronger than any external forces trying to pull them apart. And that can be any number of things. It can be temperature. You can heat them up and go from solid to liquid to gas. Some respond to absorption of energy from light, right? And they can be caused to go from solid liquid to gas. Okay. So when we see a phase change, energy in some form must be added to a solid to turn it into a liquid. That makes the motion of the molecules increase. And as they're solid, they may only vibrate, but they vibrate so fast that they may absorb enough energy to break the intermolecular bonds. And if they do that, then we have a transition from solid to liquid. And similarly, if we add more energy to a liquid, we can break those attractions completely, and we get molecules in the gas phase. Now, you may guess that the amount of energy to go from a solid to a liquid is relatively small compared to the amount of energy required to go from a liquid to a gas. And that's experimentally proven also. Other properties. Okay, if we're going to talk about measurable properties, physical properties of any substance, density is a good place to start. Density describes the mass of a substance in a given volume. So normally, what happens to most substances as we add energy from solid to liquid to gas, we start to move those molecules further apart. So if it's the same mass, but moved farther apart, that's more volume, then that means that volume is increasing, so density decreases. That's typical for a solid liquid to gas transition. Density decreases from one to the next. What we have here is an example of an anomaly. Water. Water doesn't behave that way. Solid water is less dense than liquid water. Ice is less dense than liquid. Now, of course, that's fortunate for us, right? Because if water freezes at the surface and sinks, then the temperature also freezes more water at the top. It keeps sinking. Eventually, all the oceans and lakes on Earth would be frozen solid, and we'd be in big trouble. But as it is, the density of ice is about 10% less dense than liquid. So, and less dense means the substance floats. The solid floats in the liquid. And the 10% difference is, you can see it in any iceberg, right? How much of the iceberg is above water? About 10%. Rest of it, 90%, is below water. And that's what got the Titanic in trouble. They thought they could miss the iceberg once they saw it, but actually it was the ice underneath the water that tore a hole in the bottom of the ship. So, but the trend from liquid to gas is consistent. The density of a gas is much, much less, right? At least between 4 and 5 orders of magnitude in this case. Density of the gas is 4 or 5 orders of magnitude less dense than the liquid. We've added a whole lot of space between those molecules. And we used to use a rule of thumb for liquid to gas when you compare volumes. When you go from a liquid to a gas, you're increasing the gas volume over the liquid by about 1,000 times. So if I have a liter of liquid and I turn it into a gas, it's going to occupy about 1,000 times the volume, 1,000 liters. That's why, have you ever noticed nuclear power plants? Right? They always have these huge concrete domes. Right? The reason for that is it's because of the way that nuclear power is generated in this country, and they use high pressure water. If you put water under very high pressure, then it can absorb a lot of heat without turning to vapor. Right? It'll stay liquid, and that transfers heat more efficiently than just atmospheric pressure water. The problem with that is if you spring a leak in your high pressure water system, it's going to instantly vaporize. And if there's a breach in the core of the reactor, that water is going to be contaminated with radioactive isotopes, and they're going to expand 1,000 times. So you have this concrete dome in there for containment. All right. Dipole-dipole forces. We talked about that. I described that in pretty good detail. These are permanent polar bonds in the molecule, and we know that the structure also contributes to the polarity of the molecule, right? Polar bonds, structure, asymmetrical structure will generate dipole moment in a molecule. If that's the case, then you get dipole-dipole interactions. Now, as an aside, you can also have, if you put an ionic solid into a liquid like water and it's soluble, it will break apart into its ions, and those ions will be attracted to the charges that are on the molecules of, say, water, for instance. If we put salt in water, table salt in water, then you get sodium ions, chloride ions, and they interact with water molecules. So you can have dipole ion forces also, but we're trying to stay with the molecules for the moment. And they're about 1% as strong as the covalent bonds inside the molecule or the ionic bonds between ions in a solid. Here's a description of the hydrogen bonding. I talked about that earlier. This is the strongest of the dipole-dipole interactions. And the hydrogen must be attached to a nitrogen, oxygen, or fluorine. The other atoms don't have sufficient electronegativity or small size. Remember, the small size for the proton is there, but the electronegative atom needs to be small also, so that the molecules can get close together. If you go from oxygen to sulfur, you're like that. And if you go from sulfur to selenium, you're like that. So that decreases the charge density and the strength of the dipole-dipole interaction. So we can't classify them as hydrogen bonds. Here are the London dispersion forces. One thing I didn't mention was that the London dispersion forces are present in every molecule. Right? All molecules have London dispersion forces. The question that has to be answered is, are the London dispersion forces the only available forces, or are there other forces more stronger, like dipoles, hydrogen bonding? If that's the case, then the London dispersion forces are so weak that they essentially can be ignored. But they are there always. Now, we gather information about these microscopic interactions by the macroscopic evidence. And the first, the key evidence that we're going to look at is melting points and boiling points. The stronger the intermolecular forces, the higher the melting point, the higher the boiling point, because the strength of those forces determine how much energy must be put into the solid or liquid in order to break those bonds or weaken the bonds, as the case may be. So if we see a high melting point, we know that the intermolecular forces are very strong. Here's that chart I was talking about. The hydrides of the various elements. The first group here, these are the chalcogens, right? There's oxygen, sulfur, selenium, tellurium. We see the boiling point decreases as you go up in the group. The reason for that is primarily London dispersion forces, because they're compared to other forces in the molecules, they get stronger. They're stronger with the larger molecules. Right? Remember, the larger molecules offer an opportunity for electron unequal distribution temporarily. And that's typical of all of these groups. What we see is, as we get down here and we go to oxygen, fluorine, nitrogen, the boiling point abruptly jumps up due to hydrogen bonding. And we see that we would expect, if the trend were continued, we would expect the boiling point of water to be down here around about -80, which would be a real problem for us, right? There would be no liquid water on the surface of the earth. There would be no liquid water in your bodies, right? In other words, we couldn't exist without this hydrogen bonding in water. If we go to the carbon group, the trend is consistent from tin, germanium, silicon, carbon. And methane boils at about negative 165 degrees Celsius. Okay, which molecule is capable of forming stronger intermolecular bonds? This should be an easy fix. I showed you the difference between nitrogen and water. Water is going to have the strongest because it's hydrogen bonded. Nitrogen only has London dispersion forces available for it. The structure of a molecule also determines the strength of these forces. Right? We can have C2H6O as our molecular formula, but the structure can be either the one on the left, which is ethanol, right, the drinking kind, or dimethyl ether, right? You don't want to mess with that one. In fact, it can be explosive. It's definitely flammable, even more reactive than ethanol. But the boiling points of the two are radically different. Over here with ethanol, we have available this group out here, which allows for hydrogen bonding. Right? Whereas here, you don't have that available. This oxygen is not bound to hydrogens. It's bound to carbons, which are slightly different. The difference between oxygen and carbon in electronegativities is much less than it is between oxygen and hydrogen. Plus, you got the bulk. The bulk also matters. You can't get close to this oxygen, even if you do have these lone pair electrons that give you slight negative charge. Overall, this molecule is nonpolar. All right. So which gas would behave more ideally at the same conditions of pressure and temperature? Remember when we were talking about gases last semester? What conditions lend themselves best to ideal behavior in gases? Low pressure, high temperature. But if we hold the pressure and temperature constant, which one of these would be more likely to behave ideally? Now you have to say, all right, what do we mean by ideal behavior? Ideal behavior in terms of the kinetic molecular theory. In other words, the molecules simply behave as billiard balls. They are less likely to attract one another when they encounter one another as a gas. So what you see is this dinitrogen molecule only has London dispersion forces, and it's essentially nonpolar. But carbon monoxide has a difference in carbon and oxygen electronegativities. So the oxygen side is going to be slightly negative, carbon side is going to be slightly positive. So it would be less likely to behave ideally. So the nitrogen is going to be more ideal. Carbon monoxide does have a dipole moment. It's not as strong as some, but it's there. It's permanent. Let's characterize liquids. We talked about liquids last semester in terms of just they have a relatively constant volume, but not a defined. They have an indefinite shape, but a definite volume. But there's more to it than that. When we try to compress a liquid, they're almost incompressible. That, in other words, they have low compressibility because there is some added room between the molecules. So as we push, then they can get closer together. We know that's true in nature because the density of water has been measured, compensating for salt content also in the oceans at various depths. And we find that the density of water at extreme depths, like 2-3 miles down, the density is increased considerably. So liquids can be compressed, they're just not very compressible. That's why we use them in hydraulic systems, right? In the brake lines in your car, right? Because you, when you press on that liquid, it pushes with a force through the lines to your brakes. And you'll notice if you ever have a leak in your brake line and you get gas in the line, your pedal's going to feel spongy because gas is compressible. They're not rigid, of course. They don't hold their shape. They have relatively high density as compared with gases and densities that are approaching that of solids, although somewhat less for most solids, right? With water's the exception. They have what's called a surface tension. And surface tension, by definition, is the resistance of the liquid to an increase in its surface area. Right? Now, the surface tension, this force that can be measured, is larger for high intermolecular forces. So molecules with very high intermolecular attractions have a higher surface tension. And you can see that if you've ever seen, there's this insect called a water skimmer. You can look it up on the internet. I've seen them face to face. But on calm water, what they do is they have these feet with lots of prongs on them, and they have 6 of them because they're insects, and they spread them out like this, like that. They spread their weight over the surface of the water using surface tension. And you'll see wherever their feet touch the water, there's a depression in the water. Right? If they push too hard on one foot or the other, then they'll break through the surface tension, and that foot will go under. So they're very careful with how they distribute their weight, and they can move pretty quick on the surface of the water, but they're using surface tension. Let's see. I'm not sure if I have a description of it, but hopefully we'll come to it. Another characteristic physical property of liquids that we can measure is capillary action. Capillary action is the rising of a liquid in a narrow tube. Now, try to understand that there are forces. We've talked about forces so far, but inside the liquid, that is intermolecular forces. But there are also intermolecular forces between unlike atoms and molecules. So the molecule, say in water, in a small narrow tube, there are attractive forces within the water, and there are attractive forces between the water and the glass tube. We call those cohesive forces inside the liquid and adhesive forces between the liquid and the tube. And there's a balancing act going on here. This particular example is liquid mercury. And what we see here is that the balance of forces here favors cohesive forces between the mercury atoms are much, much stronger than they are between the mercury and the walls of the container. So we don't get capillary action. In other words, you put an open tube in mercury, and it's not going to rise. In fact, it may even be depressed. And that's also the reason for the mercury meniscus being inverted. It's like this. It's convex meniscus. Whereas and cohesive forces in this case dominate over adhesive forces. Whereas with water, you get an inverted or a concave meniscus because the adhesive forces are stronger than the cohesive forces. So the forces that are attracting water to the glass are stronger than those that are attracting water to itself. Now there's another force here that's involved, and that's gravity. So when you put a small tube into the liquid, I'm going to draw it big so we can talk about it. For water, if the tube is very large, you're not going to see anything. You may see some around the edges, but the smaller the tube you get, the higher the water rises. The reason it rises first is that it's attracted to the glass more strongly than to itself. So it tries to rise up the tube, and cohesive forces draw other water along with it. So it's adding mass that's opposed to the gravitational forces are opposed to the forces drawing it up the walls. Now, it goes up so far with this tube. If we make the tube narrower, now the mass of water that's being drawn up the tube is approximately the same, but it's in a narrow cylinder, right? So the diameter's smaller, so the height's longer. and the gravitational forces are pulling down on that same mass. So it only goes up so far until there's a balance between the forces pulling it up and gravity pulling it down. And the narrower the tube, the farther it rises. Okay, another characteristic of liquids that is traceable to intermolecular forces is viscosity. And that's simply a resistance to flow. There are various ways that you can measure it. The larger the intermolecular forces, the higher the measured viscosity of the liquid. So if you try to pour honey out of a jar at room temperature, say in the summer, then it'll flow, right? But it flows kind of slow. If you try to do the same thing with water, it flows really fast. Right? So the intermolecular forces between the honey atoms, molecules, are much higher than they are between water molecules. And that's largely due to hydrogen bonding again, right? But there are more hydrogen bonds in the sugar molecules than there are in the water molecules. And it's also temperature dependent. So as you increase the temperature, you are tending to break some of those bonds, and that makes the liquid flow more readily. And vice versa, if you decrease the temperature, it's like, what do they say? It flows like molasses in winter. When you get molasses really cold, you can turn it upside down and it won't move. So viscosity is also dependent upon these intermolecular forces. Now let's switch over to solids. We've talked about liquids and some of the physical properties that are dependent upon intermolecular forces. Now, how about solids? Well, we need to classify our solids into roughly two groups. There are amorphous solids, that is, they're structurally solid, that's true. The molecules are close together, but there's no pattern, there's no order to their structure. Glass is a good example. When glass is cooled, it forms a solid, but it's an irregular arrangement of the molecules, largely silicon dioxide, but there are others in there like boron compounds and various additives, but it's largely silicon dioxide. And then there are crystalline solids. They have a very regular, ordered structure. First one that comes to mind for me is diamond. The trouble with diamond, though, is it's a single molecule, so that's not a good example. Let's try. Let's see. Well, any of the metals have a crystalline structure. Right? How about pure gold? That's a good one. They have an ordered structure, and in fact, we use that order to investigate and describe their structure in terms of unit cells. We're going to talk about that in just a second. The unit cell is the smallest three-dimensional repeating unit in a crystal. So we're gonna focus on crystals for now. And one of the models that we use to arrange these unit cells is called the closest packing structure. That is the physical arrangement of atoms, ions, or molecules. So we can cover all three of those now. That minimizes the space. If you think of atoms and molecules as spheres, right? when you put a sphere together, right, there's some open space. Or if you stack one here, one here, one here, you get some open space in there. So solids will, under certain conditions, will assume one closest packing structure versus another, depending on how they're brought together. So, and that's a whole branch of physics and engineering that people spend years working on. And it's largely understanding how atoms are packed together make for various types of metal alloys. And controlling that structure is also an engineering marvel. Okay. We can describe a solid in one of two ways, the unit cell or the closest packing structure, but they're actually related to one another. And logically, they're related because they're describing the same thing. Think of it as two sides of the same coin. Let's look at unit cells first. And the unit cells can be very, very complex, depending on arrangement of atoms and the sizes, the relative sizes of atoms can influence the way that they're structured. Like sodium chloride, right? It forms a cube. But the chloride ion is huge compared to the sodium ion. So that influences the way that they're arranged. So we're going to take the very simplest structures first. There's the simple cubic unit cell. Okay, so if we draw a cube and we put an atom at each corner, we have the simple cubic unit cell. All right. If we draw that cube and we put an atom in the center, right? Just put an atom right here in the center. Now we have a body-centered cubic unit cell. Or if we put an atom, how many sides does a cube have? 6, right? 6 sides on a cube. We can put 6 atoms, one on each face of the cube, between these. So I can put one here, I can put one there, put one back here, over here, there, and there, right? So I can put 6 of those. That's called a face-centered cubic cell. And you'll notice that there's a change as we go. There's a change in the amount of unused space. It appears to me that the largest amount of unused space is here with this simple cubic. And we use up more of that space here. But there's also one other thing I want to point out. Notice that in the simple cubic, all these spheres are touching one another. They all touch on their sides. Whereas if we put one in the middle, now they can't touch. And if we put on the face, those definitely don't allow the corners to touch. Oh, let's see. Do I have a video here? Let's see.
If you could travel within a crystalline solid, you would see the particles, atoms, ions, or molecules arranged in a regular array. Here, the spaces are greatly exaggerated, but in reality, the particles are packed close together. The unit cell of a crystal structure is the smallest portion that defines the structure. Stacking unit cells next to each other in all 3 directions gives the structure. Many elements and simple compounds have unit cells from the cubic crystal system. Let's examine the three types of cubic unit cells. All cubic unit cells have particles at the corners of a cube. The simple or primitive cubic unit cell has particles at the corners only. In reality, the particles lie as close to each other as possible. Note that the particles touch along the cube edges but not along a diagonal in the face or along a diagonal through the body. By slicing away parts that belong to neighboring unit cells, we see that the actual unit cell consists of portions of the particles. When the cells pack next to each other in all three dimensions, we obtain the crystal. If we fade the others out, you can see the original group of 8 particles within the array and the unit cell within that group. We find the number of particles in one unit cell by combining all the particles' portions. In the simple cubic unit cell, 8 corners, each of which is 1/8 of a particle, combine to give 1 particle. A key feature of a crystal structure is its coordination number, the number of the nearest neighbors surrounding each particle. In a simple cubic array, any given particle has a neighboring particle above, below, to the right, to the left, in front, and in back of it for a total of 6 nearest neighbors. The body-centered cubic unit cell has a particle at each corner and one in the center, which is colored pink to make it easier to see. With full-size spheres, you can see that the particles don't touch along the edges of the cube, but each corner particle does touch the one in the center. The actual unit cell consists of portions of the corner particles and the whole one in the center. 8/8 give 1 particle, and the one in the center gives another for a total of 2 particles. In this tiny portion of a body-centered cubic array, you can see that any given particle has 4 nearest neighbors above and 4 below for a total of 8 nearest neighbors. The face-centered cubic unit cell has a particle at each corner and in each face, which are colored yellow here, but none in the center. The corner particles don't touch each other, but each corner does touch a particle in the face, and those in the faces touch each other as well. The actual unit cell consists of portions of particles at the corners and in the faces. 8/8 at the corners gives 1 particle, and half a particle in each of 6 faces gives 3 more, for a total of 4 particles. In this tiny portion of a face-centered cubic array, notice that a given particle has 4 nearest neighbors around it, 4 more above and 4 more below for a total of 12 nearest neighbors. Stacking spheres shows how the 3 cubic unit cells arise. Arrange a layer of spheres in horizontal and vertical rows. Note the large diamond-shaped space among the particles. Placing the next layer directly over the first gives a structure based on the simple cubic unit cell. Those larger spaces mean an inefficient use of space. In fact, only 52% of the available volume is actually occupied by spheres. Because of this inefficiency, the simple cubic unit cell is seen rarely in nature. A more efficient stacking occurs if we place the second layer over the spaces formed by the first layer, and the third layer over the spaces formed by the second. That simple change leads to 68% of the available volume occupied by the spheres and a structure based on the body-centered cubic unit cell. Many metals, including all the alkali metals, adopt this arrangement. For the most efficient stacking, shift every other row in the first layer so the large diamond-shaped spaces become smaller triangular spaces, and place the second layer over them. Then the third layer goes over the holes visible through the first and second layers. In this arrangement, called cubic closest packing, spheres occupy 74% of the volume. Note that it is based on the face-centered cubic unit cell. Many elements, covalent compounds, and, as you'll see in the next two examples, ionic compounds adopt cubic closest packing. Sodium chloride adopts the sodium chloride or rock salt structure, as do many other alkali, halides, alkaline earth oxides and sulfides, and other ionic compounds. Picture separate face-centered cubic arrays of chloride ions and sodium ions as they approach and interpenetrate each other. The smaller sodium ions fit in the holes between the larger chloride ions and the NaCl unit cell. Zinc sulfide adopts the zinc blend structure, as do the copper-1 halides and several other compounds. If face-centered cubic arrays of zinc ions and sulfide ions approach and interpenetrate slightly offset from each other, each ion becomes surrounded tetrahedrally by 4 of the other ions. Note the blinking zinc ion and the 4 sulfides. You can see the relative positions in this slightly expanded view of the zinc blend unit cell.
Okay. All right, we'll talk about that in just a minute. I was trying to keep track of things here. The reason for my writing this stuff up here is that the unit cell model is one way of approaching the structure of a crystalline solid. Another way is the closest packing model, and they're related to one another. There was the video mentioned the face-centered cubic is related to the cubic closest packing model. We haven't got to that yet, but we'll show you that one. And that's another way of looking at how the solids are structured. The way they're either right on top of each other or offset, or in 2 dimensions. We build to 3 dimensions by offsetting certain ways. I've got another video that's coming up for that one. But for now, I want to digress just a moment and talk about this concept of how do we know the spacing between atoms. And now we're going to limit our discussion temporarily to atomic structures of solids, because it's easier to deal with them in terms of this model where you have solid spheres, these balls that we put together. And the metals fit into that very well. So this is one way that we tell the distance between layers of a solid using the Bragg equation. And in order to do it, we need an instrument called an X-ray diffractometer. I've used one of these things. It was ancient when I was in school, and that was 35 years ago. But what it did was, let me see if is there a model on the next? Yeah, there's a model on the next page. The Bragg equation itself relates the wavelength of the light, here the lambda, and the n is an integer, which is the I've forgotten the proper terminology. It'll come to me. D is the distance between the atoms in the layers, and theta is the angle of incidence of the impinging light rays, which are typically X-rays. In the middle. I hate it when that happens. Anyway, this is what it would look like in practice. And when I used it, I was investigating the structure of clays in soil fractions. So we would separate the soil by size, run it through a series of screens, and then the smallest portion at the bottom, in order to get the clay fraction out of it, we would have to use Snell's law, I believe, and use a settling tube, just a big graduated cylinder, and allow it to settle. And clay fraction would settle slower than the rest of them, the silt and larger particles. So after a certain amount of time, we knew that at this point in that column, there would be clay only. So we would draw off some of that clay and dribble it on a glass slide and let it dry. And as it dried, the clay plates would orient themselves and they'd lay flat against each other. Then we put it in this machine and we would scan the angle of incidence like that of the X-rays, and it would give us a trace of reflected energy on the other side. And wherever that, it would come out in several peaks. I'm trying to think, shoot. That N value, in music, it's called overtones. Right? You have the fundamental note and then you have overtones. It's the same concept with light. So what we're seeing here is diffraction. And that characteristic of light allows us to reflect light from the surface of the metal, and it will be strongest when all the reflected light beams are coherent. In other words, they add to one another. There's no destructive interference. It's all, the peak comes when you have constructive interference. And then we can relate through the Bragg equation, we can relate this angle, which is the same as that angle, and this distance between here, it can be solved from that equation. So the biggest peak is going to be the fundamental peak. This n equals 1. If n equals 2, then we've changed the angle, and now we get another peak, which is usually smaller. But it's the same wavelength. Right? We have to use the same wavelength each time. And then, okay. So what this allows us to do is determine the distance between these layers. And the distance between the layers is going to be the size of the atom, right? Because the distance is going to be half, since they're touching, it's going to be half this diameter and half this diameter, which means that the distance is the diameter of the atom. Now, that was in 2 dimensions. Well, actually, it's 1 dimension. But we can use X-ray diffraction to determine the structure of crystalline solids. Okay? If we shine X-rays through this solid, we get this diffraction pattern. Now, the real test, the real skill is involved in interpreting that pattern. What does that pattern mean in terms of the crystal structure? And this was the technique that was used to determine the structure of the DNA molecule. The real problem with DNA in using this technique was getting DNA into a regular crystalline solid. Right? Once that was obtained, then you could get the diffraction pattern. Okay, what types of crystalline solids do we have? Well, we can have ionic solids, and they were mentioned in that video. Table salt, sodium chloride, was mentioned. The ions are located at various places in the structure, and obviously it can be very complex depending on the compound investigated and its unit cell and where you can fit the various ions in their places. Molecular solids have covalently bound molecules at each of the points of the lattice. And atomic solids are the easiest to visualize. They simply have atoms at each of these structural points. Diamond is a covalently bound solid. So it is a crystalline structure, yes, but the forces holding those atoms together are not intermolecular forces. Those are intramolecular. Those are covalent bonds. So we're sort of fudging a little bit on this comparison. Whereas the sodium chloride is, these are ionically bound solids. And this ice is a molecular solid, yes. Okay. This is just a general, this came straight out of your textbook. This is a classification of solids. If we have atomic solids, they can either be metallic, they can be non-metallic, and covalently bound. Actually, diamond that has no flaws in it is a single molecule. It's an odd concept, but it's true. And then we have, what are the 8A atoms? Those are noble gases, right? 8A, those are noble gases. Many of them will form solids if you get them cold enough. And they're bound simply by London dispersion forces. Molecular solids, these molecules are bound together either by dipole-dipole moments or London dispersion forces. Either can be operating. And then ionic solids, of course, are bound by the permanent negative and positive charges. All right. Now we're going to look at, excuse me, the closest packing model. And we have the unit cell model first. Now we're going to look at the closest packing. And we have to make some assumptions, of course. One of those is that when we talk about, and we're going to use metals here as our model, we consider them as uniform hard spheres. Otherwise, the water gets too muddy and we can't figure things out. And how do spheres pack together? Right. So I've got this video. It's narrated by an Indian woman. And I'm talking about India, not Native American. So you have to tune your ear to the Indian accent. Once you do, then the progression makes a lot of sense. It's a rather long video. It's like 12 minutes, but it pulls all this model. It presents this model in a very logical fashion, and it's a good video.
The three-dimensional modes of packing can be easily understood by dividing the whole process into 3 steps. Close packing of spheres in one dimension. In one-dimension close packing, there is just one way of arranging the spheres. Here, the spheres are arranged in a row touching one another. As a result, each sphere is in contact with 2 neighboring spheres. Thus, In one-dimensional close packing, the coordination number is 2. Close packing of spheres in 2 dimension. Close packing structures in 2 dimension can be generated by stacking rows of one-dimensionally closed packed spheres, one above the other. This can be done in 2 ways: square close packing and hexagonal close packing. Square close packing. In this type of packing, the second row of spheres is placed in contact with first row in such a way that the spheres of the second row are placed exactly above the spheres of first row. In such an arrangement, the spheres are aligned horizontally and vertically such that each sphere is in contact with 4 other spheres. So, the coordination number is 4. If we call the first row as A-type row, the second row being exactly same as the first row, so it is also called as A-type. If we keep on placing such similar rows one above the other, then such an arrangement is known as AAA type of arrangement or square packing. Hexagonal close packing. In this type of packing of spheres, the second row of spheres is placed in a staggered manner such that the spheres fit in the depressions of the first row. If we call the first row as A-type, then as the second row is different from the first row, it can be called as B-type. Now, if we place a third row above the second row in the similar manner, we will observe that the third row spheres are aligned with those of first layer, and each sphere is in contact with 6 other spheres. So, the coordination number is 6. Similarly, on placing the 4th layer, we will observe that the 4th row of spheres are aligned with those of second layer. Hence, this type of arrangement is known as ABAB type of arrangement or hexagonal close packing. If we compare square close packing with hexagonal close packing, we will observe that empty spaces are less in hexagonal close packing than compared to square close packing. Now, what are these empty spaces and what role do they play in packing efficiency? The empty spaces in between the spheres are known as voids. These voids are responsible for decrease in packing efficiency of the solid crystal. More the number of voids, less is the packing efficiency of the crystal. Now, you must be wondering what is meant by packing efficiency. We have discussed about this in later part of the section. Now let us study about close packing in 3 dimension. 3-dimensional close packing from 2-dimensional square close packed layers. This type of packing is obtained by placing 2-dimensional square closed packed layer above the first one, such that the spheres of the second layer are exactly above the spheres of the first layer. In this arrangement, the spheres of both the layers are perfectly aligned horizontally and vertically. On arranging layers one after the other in this pattern, we will observe that each sphere is in contact with 6 other spheres. 4 from the same layer, 1 from the layer above, and 1 from the layer below that sphere. So, The coordination number is 6. If we call the first layer as A-type, and since all the layers are also of the same type, this kind of arrangement is known as AAA type of arrangement. On observing carefully, we will find that this arrangement has generated a simple cubic lattice and its unit cell is primitive cubic unit cell. Dimensional close packing from two-dimensional hexagonal closed pack layers. The three-dimensional hexagonal closed pack structure can be obtained by placing two-dimensional hexagonal structures one layer above the other. Placing second layer over the first layer. Let us take a two-dimensional hexagonal closed packed layer A. Notice this layer has triangular voids. Place a similar closed packed layer in such a way that the spheres of the second layer are placed in depressions of the first layer. As the spheres of the second layer are aligned differently as compared to the first layer, so let us call this layer as B-type. On observing, we will notice that not all the triangular voids of the first layer are covered by the spheres of the second layer. This gives rise to a different arrangement and different voids. Voids. There are two types of voids: tetrahedron voids, denoted by T, octahedron voids, denoted by O. Let us study how these voids are formed. When we place a closed packed layer above the depressions of the first layer, we will notice that at some places the triangular voids of the first layer are being covered by the spheres of second layer. At such places, a type of void is formed. This type of void is known as tetrahedral void, T, since a tetrahedron is formed by joining the centers of the four surrounding spheres. While at other places, we will notice that the triangular voids of the first layer coincides with the triangular voids of the second layer, such that their triangular shapes do not overlap. At such places, another type of void is formed. This type of void is known as octahedral void, O, since an octahedron is formed by joining the centers of the 6 surrounding spheres. Now, in case we need to calculate the number of tetrahedral and octahedral voids in a crystal structure, then just knowing the number of spheres will serve the purpose. Suppose there are n spheres in the crystal structure, then the number of octahedral voids generated is equal to n. The number of tetrahedral voids generated is equal to 2n. Placing third layer over second layer. Now let us place third layer over second layer. Stacking of third layer over second layer can be done in two ways. First, by covering tetrahedral voids. Second, by covering octahedral voids. By covering tetrahedral voids. The tetrahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer will get exactly aligned with the spheres of the first layer. So, if we can call the first layer as A-type and the second layer as B-type, then the third layer will also be A-type. As the pattern of spheres is repeated alternately in other layers, so this pattern is known as AB-AB pattern, and the structure formed is known as hexagonal close-packed HCP structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So the coordination number is 12. Covering octahedral voids. The octahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer are not aligned with the spheres of either first layer or second layer. So, if we call the first layer as A-type and the second layer as B-type, then this third layer will be C-type. Now, if we place the fourth layer over the octahedral voids of the third layer, then the sphere gets aligned with the spheres of the first layer. Thus, this pattern is known as ABC type, and the structure formed is known as cubic close-packed CCP or face-centered cubic FCC structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So, the coordination number is 12.
Okay, that was a marathon. um, so how do you organize this model so that it is, you can retain it? I think the logic there was progression from one-dimensional, two-dimensional to three-dimensional. And the key to look for is the shape of the voids. If you have 4 atoms surrounding a void, you get this tetrahedral void. If you have 6 atoms surrounding a void, you get the octahedral void. And there was some mention of relationship between the closest, the unit cell model and the closest, closest packing model, excuse me. And we'll see that occasionally. Let's see, the AB packing, or the second layer, is like the first, but it's displaced so that each is in the dimple of the first. This gives us the voids that are covered are the tetrahedral voids. And this generates a hexagonal closest packing, or hexagonal unit cell. Now, we didn't mention the hexagonal unit cell before. We're trying to keep it simple. But the hexagonal unit cell is simply a unit cell that has a hexagonal structure to it. And that would give rise, that unit cell is derived from the AB packing, the covering of the tetrahedral voids. If we cover the, if we produce the octahedral, if we cover the octahedral voids, then we get the ABCA pattern. And this leads to a relationship between the cubic closest packing and the face-centered cubic cells. Okay, let's see. There's face-centered cubic, and this related to the hexagonal closest packing and covering the hexagonal cells. Excuse me, not the hexagonal, octahedral voids. So there we are again with our face-centered cubic unit cell. And the coordination number. If you're involved with chemistry at all in the future, this concept of the coordination number will come up again and again. I've seen it used elsewhere. This coordination number, it simply means if you've got this one unit, how many other units are associated with it. In the and we're going to get into this at some point with well, I don't want to steal my thunder. I'll tell you what, I experienced this first with respect to when you dissolve an ionic solid in water. Sometimes a given number of water molecules will associate with the dissolved substance. And that is given the name the coordination number. And it's very consistent. And that coordination number leads to a certain spectral quality. In other words, you can see the color of the solution change when you add it to the solution, when you add the solid to the solution. So the coordination number is here used in this fashion, but it can be used in other ways also. Now, when we were talking about when the first video gave us the number of actual spheres that are contained within the unit cell, we have to consider how they're packed with their neighbors. So if we're assigning this unit cell, this face-centered cubic unit cell, how many, and their atoms, how many actual atoms are located in that cell? And we just have to count them up, right? So when we do that, we end up with 4. We end up with 4 atoms in the unit cell because we have to share with neighboring cells. And if we do the same thing with the body-centered cube, we only get 2. We get 2 atoms in the unit cell. And with the simple cubic, we only get 1 atom equivalent in the unit cell. That's important if we're going to solve a problem where we want to know something about the unit cell, say its volume, and then we want to know how many atoms are contained within that volume. We can actually calculate the density of that solid if we know these characteristics about it. We'll do one of those problems in just a minute. So body-centered, we left out the body-centered here. I don't know why that is. There's 1 in the simple and 4 in the face-centered and 2 in the body-centered. So if we're going to determine the physical dimensions of a unit cell, now we've gone back from the closest packing model back to the unit cell. If we want to determine the dimensions of this unit cell, we need to know how those atoms are arranged and something about geometry. The simple cubic is easy. Let's see. Okay, I'm gonna have to erase some of this. So if we have a simple cubic here, and we have an atom at this corner, and an atom at this corner, notice they touch. So if we want to know, say we want to know the volume of that cube, all we need to know is how long is the side. And then we just cube it, and that gives us the volume of that cube. So the length of this side depends upon the radius of the atom. If you know the radius of the atom, it should be right here. The radius of the atom here, the radius of the atom here. This is 1/2 the radius of that. Now this is, excuse me, this is R, and this is R. Then the length, that side, is 2R. Okay, that was the easy one. I had some handouts that described how you find the sides of these cubes, but there hadn't been much interest in it, so I've reserved those. I think they're in Brightspace if you want to look at them. So how do we do this for, say, the face-centered cubic cell? Well, we have to do some geometry there. And to make a long story short, the length of the edge based upon the radius of the atoms is the radius times the square root of 8. And that will give you the length of the face-centered cubic cell. I think I have the body-centered in here also. Let's see. Yeah, body-centered. The body-centered, the edge of the cube is the length that is the radius of the atom times 4 divided by the square root of 3. So with that information, and this information is contained in useful information at the back of your review document. Once we know that, and then we characterize, say, this silver metal crystal cubic closest packed structure is a face-centered cube. Face-centered cube. So we know then that the face-centered cube, if we know, actually, we're working backwards now. We're told that the edge of the cube is 409 picometers. So we'll use that information to tell us what's the radius of the atom. Right? If we go back to the face-centered cubic right here, then we're told what the length is, so we can solve for what the radius is. And that will give us the dimension of the cell. Here we go. So we're going to calculate the density of the silver metal and compare it to the experimentally determined density. All right, so the density is supposed to be 10.5 grams per cubic centimeter. Okay, remember there are 4 silver atoms per unit cell. Right, this is 1, this is 2, and this is 4. So we know that there are 4 atoms in that unit cell. That is 4 atoms per cell. So if we know the volume of the cell, we know how many atoms per volume. The volume of the cell is 409 picometers cubed. So what's a picometer? Right? A picometer is 10 to the minus 12th of a meter. 10 to the minus 9th is a nanometer. 10 to the minus 6th is a micrometer. And 10 to the minus 3rd is a millimeter. So a picometer is 10 to the minus 12. So once we get the volume, the picometer volume here, then we can calculate, which we've done over here. This is the cube of that picometer. This is equivalent to so many cubic centimeters. This is dimensional analysis. That's all that is. So if we have 409 picometers, we're looking for the volume. And since the density of a solid is grams per cubic centimeter, we want our volume to be in units of cubic centimeter. So if we say 409 picometers cubed, right? We can do this. We can convert, we can make picometers here, or we can go ahead and just chain our conversion factors. Right? So what we want here is some way to cancel picometers and give us meters, right? So 1 picometer is 10 to the minus 12 meters, but we have to cube it, right? Remember that trick? So the picometers now are out. Now we can convert this meters to centimeters. So that's 100 centimeters per meter, and we have to cube that. So now that calculation will give us this 6.84 times 10 to the minus 23 cubic centimeters. That's our volume. Now we need to know the mass. Well, how many atoms are in this cell? Right? There should be, let's see, it was face centimeter cubic, there are 4. 4 atoms of silver. What do we know that relates mass to numbers? The molar mass. So we need not atoms, we need moles. So that's Avogadro's number is mole. And then now we can convert moles to grams, right? So for 1 mole, silver atom is, let me see, look at my periodic chart. Silver is 107.87. 107.87 grams. And that'll give us the mass that's contained in that volume. Okay, let's see. Well, we did the calculation all the way through. But once you get that mass, you just ratio it to the volume, and you get 10.5 grams per cubic centimeter, which is very close to the measured value. All right. Now, we're going to stay with metals. We're going to stay with metals and consider how metals are bound to one another. Remember last semester when we were talking about binding atoms together? We had ionic bonding and covalent bonding, but I skipped over how do we get metals to bond with one another. Now we're going to talk about that. in chronological order, the first theory that was proposed was called the electron C model. And it's called a C because the positive nuclei of the metal is sort of suspended in a sea of electrons, and they're just everywhere. But that's a really messy idea. What we eventually settled on is the molecular orbital model, which is for metals called the band model. All right, so this is the electron C model, and all you had to do was just balance the numbers of charges. So this would be like a sodium nucleus and electrons. This would be like a calcium nucleus and electrons. But the molecular orbital, the band model, is more accurate. It does a better job of explaining the physical properties of metals. These molecular orbitals, and remember, when you've got a chunk of metal, you have as many molecular orbitals as you did atomic orbitals for each of the atoms. So it's a massive number. And I don't know if you remember, but the more the more molecular orbitals that you derive from a combination, the closer they get together. So that's the idea. That's why we call it a band. Electrons traveling around the metal in this crystal structure form these molecular orbitals from all of their electrons, but we focus on the valence atomic orbitals to form the molecular orbitals. And the more and more you get, the closer they get together. So all you need is by the time you get 1 mole of atoms, the band, the distance between the energy levels is so small, it doesn't take much to jump an electron from one level to the next. This is another way of looking at it. The concept of filled molecular orbitals and empty molecular orbitals. And the band gap, they call it, the energy required to move an electron from the filled to the empty is extremely small. And once it's in that, moved up into that empty orbital, it can associate with any atom, any nucleus. So that's why metals have very high electrical conductivity, very high thermal conductivity, and they form varying degrees of strong bonds. But it's easy to move them around. Actually, they're very malleable because you have this banding of energy levels and allows the electrons to move freely. You can move the nuclei around also because of that. Now, we've seen in the previous video how certain unit cells accommodate smaller atoms or smaller ions. And that concept translates well into a certain type of metal alloy. In other words, we can add either other metals or non-metals to a base metal and modify its crystal structure and how it behaves. There are 2 ways to make an alloy. There's the substitutional alloy. That is where we actually substitute a different atom for one of the base metal atoms. The best example of that I can think of is brass. Brass is copper and nickel. So we simply have copper as the majority or the base metal, and we substitute nickels in for some of those coppers. The other option we have is interstitial alloys. That is where we have these voids in the crystal structure. We can put small atoms in there. And that's the way steel is made. We take the iron structure with its voids and we put just a very few, usually less than 0.5% by mass, we put in the carbon atoms. Okay, so there's the brass example and there's the steel example. If we put too much carbon in the iron voids, then we make it very brittle. And it's good for some things, like cast iron is very good for resisting wear. That's why modern automotive engines may have aluminum blocks, but they have holes drilled in them, and we put a sleeve of cast iron in there. And that allows it to wear for thousands of miles without wearing out. This slide harkens back to the time when I talked about I tell you what, if you don't grab those thoughts when you have them, then they're gone. Shoot, I'll think of it in a minute. Diamond is this structure, right, with its covalent bonds. Graphite is a hexagonal structure in layers, which are very strong bonds. These covalent bonds between the atoms are very strong, but between the layers are weaker bonds. And what kind of bonds would these be? Well, they would have to be London dispersion forces, because this graphite structure, they're all the same atoms, so they have to be nonpolar. That means the attraction between them has to be very weak, London dispersion forces. That's why graphite is often used as a dry lubricant. I mean, you have the very strong plate structure of the graphite, which can resist forces, but they can slide past one another very easily, and they're a good dry lubricant, right? Not a wet lubricant like oil, which will accumulate dust. These dry lubricants are very good for situations where you don't want dust to get in and contaminate the space. We used to use graphite in our control cables on our motorcycles, right? It comes in a can with a long, thin tube, and you just stick it in there where the cable goes in and squirt it, and it lubricates the whole cable. Allotrope. These are allotropes of one another. They're the same element, but they're different structures. Diamond is an allotrope. Graphite's an allotrope. We mentioned others like buckyballs, Buckminster fullerene, or nanotubes. They're all the same element, but they're different structures. Diamond has a very wide band gap between the filled molecular orbitals and the empty molecular orbitals. That's why diamond is a very poor conductor of electricity or heat. It's virtually an insulator. Other crystals are not quite as good an insulator. So the gemologist at your, say, Kay's Jewelers will take a device and just touch it to the diamond or the stone, and it will measure the thermal conductivity of that stone, how the heat wicks away from the source into the stone. And if it gives you a very high conductivity, it's not diamond. If it gives you a very, very low and they calibrate it, then you have diamond. And this technique was used on a gem that my wife had gotten from a friend who thought it was tanzanite. You know, it's beautiful blue. The person that sent it to us, all we had to do was pay for shipping, and it was like a couple of carats, was tanzanite. So we were showing it to the jewelers one day, thinking about getting it set in a ring maybe. And they said, oh, that's a beautiful diamond. I said, no, that's supposed to be a tanzanite. So they got out their device and put it on there. Sure enough, it was a diamond. So next day, we contacted the State Farm and got a rider on our homeowner's policy to cover that diamond. So this is what we see. Remember at the toward the end of our last semester, we talked about sort of a hybrid molecular orbital and valence bond theory. So we get these hexagonal structures that are bound covalently to one another, and they have these donut-shaped delocalized electrons. Well, those electrons distribute themselves unevenly over time, right, and produce the potential for these London dispersion forces. And that's what attracts one layer to the other, even though the attraction is very weak. Talking about solids some more, there's a classification of solids. This is operationally defined. So these solids have certain characteristics that make them ceramics. Typically, they're made from silicates, clays and silicates. And they turn out to be, they're non-metallic, right? They're very, very strong, especially in compression, but they're brittle. So if you have a shear force on them, they will crack and break. But they're very resistant to heat and very resistant to attacks from chemicals. The technical term for that is refractory. They are not easily attacked by chemicals. That's why ceramics form the basis for heat shields on various rockets. You just have to formulate them correctly and fire them at very high temperature. They go through a reaction, they call it a pozzolanic reaction, that changes their crystal structure and establishes this ceramic character. More solids. The semiconductor industry is based upon how we form these. Well, if there were metals, they'd be alloys. But since the semiconductors are typically nonmetals, what we find is that there are basically two types of semiconductors. And you need a host element. We typically use silicon. So very pure silicon, 99.999% silicon is the base. And then you exchange selective elements for the silicon atoms. And that forms the basis for the semiconductor. They're called semiconductors because they're not full conductors, not like copper wire or aluminum cable that conducts electricity very easily. They have a controlled conductance. So N-type semiconductors are, N stands for negative, which means the doping element has at least one extra electrons than the silicon. So if you look at your periodic table, which ones have more electrons than silicon? The ones to the right. So phosphorus to the right, arsenic to the right would have an extra electron. So you dope that in there and you get an extra electron that's relatively free to move if the force is strong enough. And that allows it to conduct electrons in various directions. The p-type semiconductors, P stands for positive, are deficient in one or more electrons compared to the host element, which would be silicon in this case. So to the left of silicon would be aluminum, boron, gallium. You could dope your silicon with a prescribed amount of those elements, and that would be deficient in an electron. So if we look at them in terms of filled molecular orbitals and empty molecular orbitals, the excess valence electrons in the N-types are close enough to the molecular orbital conduction band so that all we need is just a little push and we can get them there. But if we don't have enough push, then they don't move. So that's the basis for the binary code, zeros and ones. The p-type semiconductors are deficient in electrons. So the concept here, the way we rationalize it so we can make sense of it for practical purposes is we don't say the electrons move, we say the holes move. So instead of the electrons moving up into the molecular orbital conduction band, the holes move down into the filled molecular orbital band. And then we structure our semiconductor chips with a combination of N-type and P-type semiconductors and various other things. Okay, so this is what it would look like with arsenic. Doping would give you the extra electrons. Boron doping would give you the holes. Ionic solids. Okay, now we're going to get to solids like sodium chloride or calcium chloride, magnesium chloride that I've been throwing out on the ice on my walk. They have the ionic solids are composed of positive and negative ions. They have very high melting points held by strong electrostatic forces that are well defined with Coulomb's law between the cations and anions of the solid. I will say this, that ionic solids are all insulators. That is, if you put a positive electrode on one side of a crystal and the negative on the other side, you will not get conductance because those ions are locked in place when they're in the solid. The only way to make them conductors is to melt them or dissolve them in a liquid so that the ions are now free to move. Once the ions are free to move, then they will conduct electricity. So let's go back. Melting points. They have very high melting points. So what's responsible for differences in the melting points of various ionic solids? Well, two factors, and I've mentioned these before. We're going to go over them again. One is the size of the charge. Coulomb's law says that the force attracting a positive and a negative charge, or repelling two positive or two negative charges, either way, that force depends upon the size of the charge difference. So the attractive force between sodium and chlorine is small compared to magnesium and oxide, simply because of the size of their charges. The other is the distance between them. Again, sodium and chloride are relatively large. So the distance between their centers is large, and that decreases the attractive force. Whereas the distance between the magnesium and the oxide ions is small by comparison, and the force is increased. So you would expect the melting point for magnesium oxide to be much higher than it is for sodium chloride. Okay. This was discussed in that video, right? If we are in two-dimensional structure, we see these trigonal holes. When we offset one layer of spheres, we produce a trigonal hole. If we go to 3 dimensions, where we cover the trigonal hole with an atom, then we get the tetrahedral hole. If, on the other hand, we take a trigonal hole and we offset the next layer, we can produce this octahedral hole. And it's simply octahedral because at the points of all the imaginary shape, you have 6 points, which gives you 8 sides. That's octahedral. Now, this is, I don't think, I should remove this slide. This is not a fair comparison when you look at the size of the holes. Right? Trigonal is a 2-dimensional hole. tetrahedral and octahedral, those are three-dimensional, so we could compare those rationally. The trigonal shouldn't even be there. The octahedral hole is bigger than the tetrahedral hole. So wherever you have octahedral holes, you're wasting more space. And this is just a compilation in this graph of the various types of structures, what they're made of, how they're bonded together, their properties, and some examples. So we're not going to go over this because we've already beat that horse to death. This is just pulling everything together in one place. Now we're going to talk about various physical properties based upon what we know about the intermolecular forces that are holding them together. The first one we want to look at is vapor pressure. If you put a liquid in an open vessel and it has any degree of volatility at all, in fact, even mercury has a certain volatility, you will get a distribution of energies of the molecules or atoms in the liquid, right? They will have, we can express it this way in a graph, right? So if we have, this is energy, and this is numbers. So we come along and we have, say, a distribution like this. Most of the atoms or molecules in the liquid will be in this range. They'll have a certain amount of energy, but there's some that have low energy and there's some that have high energy, very high energy. Those that have high enough energy may have enough energy to actually leave the surface of the liquid. Okay, and that's what we're showing here on the left. Now, if you leave it open, right, and eventually all that liquid's just going to evaporate. But if you stopper the container, if you confine the liquid and the gas in its headspace, then initially you get evaporation only. But eventually you get enough of those, you get enough of those molecules in the headspace so that now some of them start to return. So you get a distribution of energies of the gas molecules also. And those that strike the surface of the liquid and have the lower level of energy may return to the liquid. And if you wait long enough, then you notice that the volume of the liquid decreases as you increase the number in the gas phase. And eventually you reach an equilibrium. You reach a physical equilibrium where evaporation and condensation rates are exactly equal. Now, this varies depending on the nature of the molecule. If you have, let's see, am I going to talk about here? Well, this is an idea. The rate of evaporation is constant. The rate of condensation increases until they both balance. That's all this graph is showing. We don't observe any change in the volume of the liquid, but the evaporation and condensation are occurring at furious rates that you could calculate. Yes, we have calculated them, but they're very fast. I will say this: the differences of vapor pressure, which you see with various liquids, is dependent upon the strength of the intermolecular force. So if the intermolecular force is very strong, the vapor pressure would be low. So high force, low vapor pressure, because it's more difficult for the molecules to leave the liquid. Whereas if you have very, very low force holding the intermolecular force holding the molecules in the liquid phase, you have more of them in the gas phase. That will increase the vapor pressure. Now, how do we know their pressure? Because we have a gauge that's stuck in the top. And according to the kinetic molecular theory, some of those gas molecules are striking the gauge. And that gives us an indication of pressure. More of them striking the gauge at a given pressure gives us, at a given temperature, gives us more pressure. Okay, what's the vapor pressure of water at 100 degrees C? 1 atmosphere. Because 100 degrees is the boiling point at 1 atmosphere pressure. What this slide is trying to show is the difference in vapor pressures with the difference in molecules. So here we have a vacuum and we have 760 torr on this barometer. If we have water up here, then it will vaporize to a point that will give us 24 torr. And this is at a standard temperature, which is 25 degrees. This is ethanol. It gives us a higher vapor pressure because the intermolecular forces holding the liquid together here are much lower than they are for water. So this gives us 65 torr as a vapor pressure. But if we change the structure of that molecule, actually it's not the same molecule, excuse me. This is diethyl ether. Diethyl ether will give us a huge vapor pressure because the forces holding that molecule together, the intermolecular forces, are very weak. So a lot of it goes into the gas phase and produces a very high vapor pressure. All right. Vapor pressure does increase significantly with temperature, and that's logical. If you're adding more energy, then we shift this curve over here, right? If we only need that much energy, we shift the curve by adding more energy to the substance, then we shift more of them into the in the range which they can leave the surface of the liquid. This is just comparison of different liquids, right, with temperature. Increase the temperature, and we get to, when we reach 760 torr, that's the boiling point. So water occurs at 100 degrees. Ethanol boils at a lower temperature, 78.4 degrees Celsius. And diethyl ether boils at 35 degrees, roughly. So this is how we distill ethanol from a mixture of water and ethanol. So if you have your corn mash been fermenting for a couple of weeks and you're a moonshiner, then you heat it up and the ethanol comes off first. Well, actually, the ethanol comes off second. First thing comes off is methanol. Methanol has a lower boiling point than ethanol. It's also poisonous. So the first fraction that comes off of your still, you throw it out because you don't want to blind or kill your customers. And then you collect the ethanol. And most of the water stays behind. So the relationship between vapor pressure and temperature is determined by this term right here, delta H, the enthalpy of vaporization. So it tells us how much heat is required per mole to vaporize, to go to the gas phase. Now, this equation is accurate, yes, but it's not very useful. So what we want to do is rearrange things, and we end up with this equation down here, the bottom. This is the Clausius-Clapeyron equation. Well, one form of it, I should say. The advantage to this equation, the natural log of the vapor pressure equals minus the enthalpy of vaporization divided by the gas constant times the inverse of temperature. And this temperature has to be in Kelvin. And then plus a constant. So what does that look like? It looks like a straight line, right? This is Y. This is the slope of the line. And this is the X value. And this is the Y-intercept. So if you plot it that way, if you measure the vapor pressure for different temperatures, then the slope of the line will give you the heat or the enthalpy of vaporization. And that's what we're looking at here. A more useful form of the equation is if you measure the vapor pressure at two different temperatures, then you can use this bottom formula, which is just simply a rearrangement of the Clausius-Clapeyron equation. And the vapor pressure of the first temperature is related to the inverse over here, minus the inverse, and the second temperature is here. Typically, the second temperature is the higher temperature, but it doesn't have to be. And that way, you can measure with two temperatures, vapor pressure, and determine the heat of vaporization, the enthalpy of vaporization. Temperature in Kelvin, obviously, and the R value is the one that has energy with it. Since this is an energy term, we use the energy equivalent of the gas constant, 8.3145 joules per K mole. So what would it look like if we have, we measure the vapor pressure of water at 25 degrees, and the heat of vaporization of water is 43.9 kilojoules. What's the vapor pressure of water at 65 degrees, right? This is like any other algebraic expression. If you know all the variables, if you have values for all the variables except for one, you can solve for it. And that's what we've done here, right? So there's your equation. And this is the what we know, right? The first temperatures gives us a 23.8 torr. And we don't know this value right here. That's the unknown. So it's equal to this heat of vaporization. And we have to modify the units because this is kilojoules and we need joules, right? We can't mix apples and oranges. So this is 43,900 joules per mole. There's the gas constant. And here's the inverse of the second temperature minus the inverse of the first temperature. And we just solve for our unknown. And it turns out to be 194 torr. Now, the vapor pressure can be, since we're ratioed here, the vapor pressure can be any value. Torr would be millimeters of mercury. We could use atmosphere's pressure. It'd work just as well. But the temperature has to be Kelvin. All right. So here's the heating, what we call the heating curve for water. You can do this for any solid liquid gas transition. What we're seeing here is as the temperature increases, if we only have solid water or ice, then the temperature gradually increases as we add heat. Once we get to the melting point, think of it this way. The energy that we're putting into the ice is going into kinetic energy of the molecules so that they're vibrating faster. But once they start to break loose into the liquid phase, now the energy is going into making liquid, and the temperature remains constant. So as long as you have ice and water together, the temperature is going to be 0 degrees. Once we've got it all in the liquid phase and we continue to heat, then the heat goes into vibrating the molecules again. And that increases to the point where we get steam. Once you produce steam, now all the energy goes into producing steam and phase change. Once it's all steam, then you can heat the steam up. All right. So what you're going to have here, if you need to calculate where you can go on this curve with a certain amount of energy, then you need to know how this transition occurs, how this transition occurs, how this one occurs, mathematically speaking, and use up your energy as you go until you get to the point where all your energy is used up, and that'll tell you where you are in the curve. And we're going to work a problem like that in just a minute. Here we go. So which would be larger for a given substance? The heat of vaporization we looked at with the Clausius-Clapeyron equation. But there's also heat of fusion. That is, when we change a solid to a liquid, that's the amount of heat in terms of joules per mole of substance that is required to go from solid to liquid. We call it heat of fusion because it's the same amount of energy to go either way. If we put energy into the solid, it makes liquid. If we take energy away from the liquid, it makes a solid, and they're equivalent numerically. So we call this one heat of vaporization, this one heat of fusion. And the heat of vaporization takes much, much more energy than the heat of fusion. Oh, I didn't explain why. Well, for fusion, you're simply weakening the bonds so that the molecules can move past one another. But with heat of vaporization, you're putting enough energy into the substance so that you can actually break them away from each other. Okay, phase diagrams. Phase diagrams are, for a given substance, relate temperature to pressure and where the phases occur. Right? These phase diagrams can be extremely complex. So I'm going to give you the very simplest form. And we're going to look at characteristics or points on this graph that are important. Triple point, critical point, phase equilibrium lines, and that's coming. So here we go. This is for carbon dioxide, right? Start with solid carbon dioxide, right? Dry ice. That would be in this region. This is solid. If we have a temperature less than this value and a pressure of this value, so low temperature, high pressure, will give you the solid in this region. If we have a temperature this high and a pressure in that region, then we get liquid up to a point. I'll discuss that in just a second. If we have this temperature this high, but the pressure is low, we get a gas. And the line that divides the two is, on the previous slide, the phase equilibrium line. Right? So if we're at this temperature and this pressure on this line, that means that there is, in this case, solid and gas together at the same time. If we're on this line, that means there's solid and liquid together at that temperature and that pressure. And if we're here, there's liquid and gas together. Now, there's one point on this graph at a given temperature and pressure where all three phases exist at the same time. That's called the triple point. So at this point, at minus 56.6 degrees Celsius and 5.1 atmosphere, we have gas, liquid, and solid all together at the same time. The other important point is to notice here. This is called the critical point. What we're saying is that above that temperature and above that pressure in this region out here, you will have a fluid, but it's indistinguishable from liquid or gas. It's a supercritical fluid. That's what we call it. Excuse me. We used to use supercritical fluid, in fact, carbon dioxide. If we heat it up to a certain temperature and put enormous pressure on it, right? Look at this, 72.8 atmospheres, very high pressure. We create this supercritical fluid, and it has some very interesting properties. This supercritical fluid can be added to biological material. It will penetrate the cell walls without disrupting them. It will dissolve the contents and extract them out of the cell without damaging the chemicals that you're withdrawing from the cell. And then once you remove the solid portion, the cells that have been extracted, and just release the pressure, then the CO2 evaporates and you have pristine, usually secondary metabolites. The advantage to that is the extraction process is very mild. If you have some chemicals that biochemicals in your cells that you want to extract and you don't want to modify them with high temperature, then this is a good way to extract them. Otherwise, you've got to extract by other means, which uses much higher temperatures, like a oxalate extractor, and I can, anytime you want, I can describe what that is, but it uses high temperature, and some compounds that you want to extract can't stand the heat. Okay, this is a phase diagram for water. Remember, water was kind of odd when it comes to density, right? Ice is less dense than liquid water. Well, when we investigate water in terms of pressure and temperature and its phase changes, we find that the slope of this line, the solid liquid equilibrium line, is not like this line. Notice the slope for most substances for the solid liquid is positive slope. For water, the slope is negative. So what does that mean in a practical sense? Well, at any given temperature, if you decrease the pressure on liquid water, you transition to solid. You make ice. Whereas if we did the same thing with carbon dioxide, we would go from solid to liquid. Okay, here we have a comparison of these various physical properties. And what we want to do is relate them to the intermolecular forces. So, if the intermolecular forces of the molecules increase, what happens to each of the following? If we increase the intermolecular forces, it takes more energy to boil. So the boiling point should also increase. Viscosity. If we increase the molecular forces holding the substance together, then the viscosity increases. A measurement of viscosity, a higher number means more viscous. That is, it doesn't flow very well. So that's also an increase. Surface tension. Surface tension increases with intermolecular forces. I didn't describe surface tension very well. If we have a liquid, here, you've got molecules at the surface, and you got molecules below, like that. What are they doing to one another if they're in the liquid phase? Well, they're attracting one another, right? There's a force of attraction. So this particular molecule is being attracted all around it, like that. Relatively evenly attracted from all sides. But at the surface, you've got attractions this way and this way and this way, but you don't have attraction at this on the surface. So the attractive forces between these molecules are compounded. The total amount of force is applied to these at the top, the same as at the bottom, but now it's spread this way and that way. So there's a stronger force holding those molecules together at the surface. And that's what the water skimmer is taking advantage of. You can push on the surface and it will push back. You can also take a petri dish of water, make sure it's really calm, and take a small needle and gradually lower it to the water. And when you turn loose, it should sit on top of the water due to surface tension. Okay. Now, enthalpy of fusion, heat of fusion. What happens if you increase the intermolecular forces? It should take more heat to turn the solid into a liquid. That's the increase. Freezing point. Well, the freezing point, as the strength of attraction increases, the freezing point should also increase. In other words, the freezing point, I don't know what it is for nitrogen. I know the boiling point for nitrogen is minus 195 degrees C. I think just slightly below that is also the freezing point. So let's say minus 200 degrees. Very weak forces among nitrogen molecules. Whereas the water molecules, very strong attraction, their freezing point is 0 degrees Celsius. So that's a 200-degree difference. Vapor pressure is the opposite. As you increase the forces, the vapor pressure decreases. And the heat of vaporization, for similar reasons to the heat of fusion, is also increases. So of all these, the only one that is inversely proportional is vapor pressure. All right, that takes care of chapter 10.